recorded live at Town Hall here at Hillier Measurements. This is AE Squared. In case you weren't aware of our company, Hillier Measurements, we're in the business of designing and manufacturing custom test equipment, mostly for mission-critical things. Think like planes, 5G, medical devices, things of that sort. One of the things that we struggle with, have historically, is that our clients tend to bring us in at the end of their schedule, and oftentimes they're late. And so the test part of what we do ends up getting squeezed at the end of the program. And then as we get started, as we all know here, sometimes we can suffer from the same problems. The reason why I share all of that is that a couple of years ago, as I was thinking through how we address and perform better as a company, I was referred to tonight's guest's work. And since then, I have read and reread 3 of his books. I think you've written 3. And suffice it to say today, I am not just a fan, but a true evangelist of the work of Don Reinertsen. And so we are incredibly excited to share Don Reinertsen here at Hillier with our staff, but also you watching online. But before we introduce you to Don, I did want to fill you in. Here's a little of what's going on here at Hillier recently.
What we do here is a service. And when you look at the passion that ultimately creates the culture, that culture reflects, in fact, on how we perform to the most important part of our business, which is our customer. And therefore, there is a transparency, and equally important, there is the commitment to their success, which translates to our success.
Our customers want to work with us because, first of all, we're very good at what we do. But maybe more importantly, we try to work with our customers as partners, understanding not only their written requirements, but really what are their overall goals for technical, their business goals, what is driving them. We go well beyond simply reading the letter of requirements and proceeding with the design. We work hand in hand as partners.
We are Hillier Measurements.
We are Hillier Measurements.
We are Hillier Measurements.
We are Hillier Measurements.
Welcome back. It is my distinct pleasure to welcome to the AE Squared, Mr. Don Reinertsen. Don, so great to have you. Don, I've been looking forward to this for the last 2 years. You have been seriously living rent-free in my head, and it is a pleasure to have you here. It's a true honor. So, for those who aren't familiar with you or your work, could you take a second and most of our audience are engineers or business owners or whatnot. What is a company owner or a product developer or whatnot, what do they look like in their business today that really points to they need to meet you and the work that you outline in your books? What does their world look like before engaging in flow?
I would say that there's a lot of stuff that is done by tradition of we have always done it this way, or I read about how a project should be managed, or I read about how Toyota reduces variability and Deming says variability should be low and things. But they've been basically processing these ideas non-critically. And they're not thinking about why do they work sometimes and not work other times. And I think, that to me, one of the biggest issues is that they will always tell you that we're trying to deliver value to shareholders or produce stuff that has more value than it costs to make and stuff like that. And then you say, well, so what causes you to make money in your business? And things, do people buy your product because a guy I worked with at HP used to say, my definition of a good product is I have it and you don't. Now, he was a big believer in cycle time as
Sure.
adding value, and HP placed a lot of emphasis in those days on cycle time. But I'll encounter people who'll say, oh, I think we should shorten our development cycle, and I'll ask them, I said, well, what makes you think you will make more money with a short development cycle than with a
what it
long
is.
one?
Right.
And the answer is, I don't know.
Hadn't thought about that.
I read in a magazine that shorter was better.
Right.
And so there's a lot, there's a huge amount of, I read or heard something that was a plausible narrative that has people chasing after stuff that actually doesn't make much engineering sense. And so I tend to, I think probably the biggest thing about my approach to the problem is I like to view it as an engineering design problem. Is that we can think of the design of a development organization, the design of a development process, as if it was an engineering problem instead of being a problem in a different domain.
So, interesting. So when you talk about Deming and Toyota, obviously, in my industry and many others, the buzzword of the day is to take an agile approach to product development. And exactly as you say, a lot of folks, I went through that, trying to apply it, not really understanding what it is, but just the promise that things would be better, right? Our struggle was, it seemed like Agile made sense and you could accept it as long as you were developing a website or a full stack software, but the minute you tried to design physical things, it became very, very cumbersome at best and confusing most often in terms of how do I measure what better looks like? So within the construct of what you're doing, making this into an engineering project, what are the measurement devices that you would recommend someone new to your system look at? How do you start that process, looking at it from an engineering perspective?
Yeah, well, usually I start with often people will say, I need certain metrics. They say, oh, let's go to a metrics conference and hear about good metrics to use. And I would always ask them, I'd say, well, okay, so you're not really interested in metrics. What you're really trying to do is design a control system, right? Because, if metrics caused behavior change, everyone who bought a bathroom scale would be losing weight.
Right.
It's got to be part of a closed loop system. And then the question is, if you're designing this closed loop control system and you're trying to pick a parameter that you're going to control, you probably want to pick a parameter that is causal to economic success. You don't randomly pick parameters. And so you got to, because if the intent is to influence economic outcomes, you need to ask which parameters influence the economic outcomes, and therefore where do I put in and design the control loops. And the huge omission that we saw for decades was people were spending, I would work with a design team and I do an analysis on the part of the original one I did back in '83, is we saw that if they overran their development expenses by 50%, it would cost like 3% of lifecycle profit. If they missed let's say if they missed their product cost by 10%, it would cost 50% of lifecycle profits. So clearly they were in you take
Right.
cycle time out of this for now.
Right.
Even in that particular case, you'd say that product cost, bill of material cost, had far more leverage than development expenses for that company. And then I would ask them, how are you spending your control over it? What percent of the effort you spend on control is devoted to the parameter of expenses versus the bill of material cost?
Right.
So what you would discover is once a week they were reporting on where were their current expenses, what's their expense budget, how are they going to stay within budget over the entire program. So weekly effort on tracking all of the expenses and things. they didn't even do a roll-up on bill of material cost until they were probably a third of the way through the program.
Right.
And so there were parameters that had enormous economic leverage that they were not paying any attention to. And you suck away all of the energy and time on parameters that have insignificant economic impact, and it means you're not going to control the other ones.
Right.
And in contrast, you would look, for example, at an automotive company, and they do really good cost-focused design, but they're tracking the cost of each part down to the 3 decimal points from the very beginning of the process. They have control systems that are really focused on the things that have the most impact. And I think, ultimately, when you start looking at a lot of these choices, you look at choices of how do I organize a team? Well, we've had functional organizations, we've had cross-functional teams and things like that, but basically every organization design choice is a choice to strengthen certain communication links, and you automatically weaken other communication links when you strengthen the others.
Right.
And so the organization design question is, which of the communication links am I trying to optimize? Right. If I've got terrible communications between manufacturing and engineering and things like that, I need to have an organization structure where I have manufacturing people located in engineering and engineering people located in manufacturing. I need to work on the links that have a lot of information that needs to flow and a high tendency to corrupt that information. And so rather than the traditional approach of draw an org chart and see what the flavor of the month is,
right,
I think it's much better to go back to basic principles of saying these organization choices are creating needs for communication. Where do I want the really good communications to be within this system?
Right. So embedded in what you just said there, would it be safe to say that the first principle metric to think about in all design organizational choices and whatnot is, what is the incremental impact on life cycle profits? Is that the basic
That's
first
what
principle?
I've found that, I use cumulative life cycle profit.
Right.
And it's really worked well for me for about 30 years. And it works well because when you ask people, well, why are we doing this? Why are the shareholders giving us money to design this product and things like that? And the notion is that the business is sustainable if giving you money produces money in return.
Right.
And things like that. We're ultimately developing products not to win awards. We're doing it to make money.
Profit.
It's a profit-making business and things like that. So certainly one of the first questions you need to ask is how do we make money in this business? And when you do that thoughtfully, you look at before we sat down here, I was talking a little bit about HP. You look at how much money is made on a printer and how much money is made on the cartridges that are sold for the printer or the cartridges for the. Do you think that is an accident that they stumbled across that? Or might there actually be a thoughtful design behind that product and pricing structure and system in order to create that annuity of profits from the cartridges and inkjets?
Now, core in your work, and this is probably the thing that most affected my thinking early on, was the concept of thinking about and measuring critically something you call the cost of delay.
Yep.
So can you spend a little bit, because most of our listeners perhaps have not met you, talk to us a little bit about cost of delay. And I know in our experience, it was shocking when we started to think about that, its impact, but also how it drove our thought process in how we approach design decisions.
Okay. So a lot of times when I use cost of delay, I'm using it in a very sort of well-defined, narrow way. A lot of people will take that label and hang it on a bunch of other things.
Right.
But in my world, the way we think of cost of delay is we say, if something happens on schedule, how much money do I make over the life of the product if I do that job on time? And how much money and then I also calculate how much money I make over the life of the product if I do that job 60 days late.
Right.
And the difference between those numbers is the cost of being 60 days late.
Right.
And so and that conceptual analysis, it's the difference between something happening on time versus at a later time, can be applied in a vast array of things. Like for example, a lot of times in production processes that have a deadline where, Boeing has to ship a plane on a certain date and things like that. And I'd work with aerospace suppliers, and they would say, well, what's the cost of delay on a product that is never late? We make a hydraulic cylinder for Boeing. We will do anything in the world possible to prevent delivering it late.
Right.
I say, okay, so that event is never going to happen and things like that. Why don't we look at some of the upstream milestones in your program and ask the same question? Your plan is to have a release to manufacturing 4 months prior to delivering the product to Boeing and things like that. What's really happening is you're late releasing it to manufacturing, and instead of having 16 weeks, they have 14 weeks or 12 weeks or 10 weeks. And then you say, okay, so when we slip that release to manufacturing, what happens in manufacturing? Are there any costs that appear that would not have been there if we had done it on time? And the answer is, then we have to start expediting in material. We don't have enough time to do the layout designs for the factory floor. We don't have enough time to do our fixtures and tooling and things like that.
Quality goes down.
We have we have rework. You can see in the work orders that we have variances that are present because we weren't able to. So we're dumping all of this money into factory overhead for variances because we didn't give the manufacturing people enough time to do their job.
Right.
And my argument is, you can really hang a price tag on not delivering to manufacturing at the right time. Right. And you can use that price tag to make choices about how hard you're going to work to deliver on the right time. Are we going to end up doing risk buys of material even though we don't know whether we're really going to need it, because that will protect us from being late on things. So you can inform a lot of decisions. The cost delay is really a general purpose tool you can use for essentially any event that has the potential to be later than planned, and to say, do we have any information that would allow us to estimate the consequences, the financial consequences of being later than planned?
Is it consistent? I know it has been in our experience that once you get a sense of what the cost of delay, the pragmatic decisions about what to do to address those delays, often the decision you arrive at is seemingly counterintuitive from decisions you would have made had you not thought about cost of delay prior.
You're right, is that what you'll often find when you have a way of measuring the cost of delay, it ends up changing the way you look at a bunch of problems. Like, long ago I was working with a company that they were making these big, expensive machines. They were, sort of factory automation equipment and things. And they would build, it was expensive to build a prototype. It cost like $200,000 to build a prototype. So they would build a prototype, they'd use it as a beta unit, they would put it out on the customer site. And then the unit at the customer site would end up having a problem, and they try to fix it without going to see the customer, but sometimes they'd have to go to see the customer, they send the people down, they would fix the problem. And then, and the debug phase on the customer site took a lot longer than the debug would have taken in the factory if they had the machine sitting in their lab. And so somebody said, well, look, instead of just building one of these prototype machines, why don't we build a twin
Yeah.
that we keep back at our own facility? Yeah, it costs us an extra
Another
$200,000, but it means we can troubleshoot the problems much faster. We can get that beta unit sort of accepted by the customer much faster in the process.
Get to
It
market
It had
faster, yeah.
huge dividends in terms of being able to improve the process. But in a traditional mindset where you said, I'm only looking at the expenses, I'm not looking at the speed of my development process,
Right.
it had never occurred to anyone, why don't we build a twin of the beta unit so that we can do things cheaper and faster?
Is there a place in this whole discussion about cost of delay to assign and account for the opportunity costs of delay as well? One of the things we struggle
Yeah,
with
yeah.
is with finite engineering development resources. If I'm late a month, well, that is a month that I'm not extracting financial value from my client from. It's also a month that I cannot assign that engineering resource to another client's work that I can. So I typically find that if I have direct expenses of labor of $10,000, I'm actually exacting $20,000 of loss if I look at the opportunity cost as well. Is that valid, or am I being a little painting outside of the lines
I
there?
think it's dangerous.
Is it?
Yeah, the question has come up over the years. You're not the first person to ask it, and
Right.
things like that. The problem is, and you'll see it, for example, in a similar conceptual case of where you have a platform product and derivatives based on the platform. And you say, well, the cost of delaying the platform is not just the platform, but it's all of the derivatives that are going to come from this. And the question becomes, okay, so then when we calculate the cost delay, should we include the children and the grandchildren
Yeah.
and the
Cost of delay
great-grandchildren
becomes infinite.
and
Yeah.
things like that? Now, in general, I don't recommend using the consequences on the other program. I recommend you take the other programs and view them as a separate decision of, is it cost-effective for me to acquire resources to do those other programs? What is their cost of delay, and should I be expanding my engineering organization to do those other programs? I think it's better. It really can lead to, I think, bad decisions, because you can have something really great that is being blocked by something else. And in reality, your decision is, if you've got a really great thing that is being blocked, you probably ought to be starting that now.
Right.
You probably ought to be pulling resources off the not great thing so you can
It's
do
created the stall.
Yeah,
Yeah.
do the really great thing, because otherwise, the not so great thing ends up, directly delaying the great thing.
Or the architect, which what we are focused on is how do you architect a system that allows you to work around a delay instead of stand behind it?
Yeah.
Which really
yeah.
takes us to queuing theory,
Yep,
right? Which is another large part of your book, and I'll get back to batch size in a second.
yeah, and non-intuitive part for most people.
Exactly, but it's non-intuitive, but innately we all understand it. If we've ever been to Costco on a Saturday or stood in a fast food line, we all engage in queuing theory every day. But it's kind of eye-opening to think about what we innately understand, but apply it towards our process flow, especially when we think about designing, the work product being invisible within design. Can you speak a little bit about that?
Yeah, I mean, I often, the most accessible example of queuing theory that has, I think, universally worked for me to end up explaining, how queues work to people is traffic at rush hour on a crowded highway. And sort of, I make I use the analogy, I say, okay, so you're already familiar with queuing systems. Let's take a 4-lane highway, I remove 1 lane of capacity at rush hour. what will happen to cycle time? I've removed 25% of the capacity. Does that mean cycle time goes up by 25%? No, it doubles or triples.
Yeah.
And then I say, okay, what happened if I removed 25% of capacity when the system was lightly loaded at 3 a.m. in the morning? No change in cycle time. So I say, okay, so your intuition says that in a queuing system, changes in loading have a nonlinear impact, and that nonlinearity depends on capacity utilization. Okay, so now let's look at what you're doing in engineering. Engineering is another queuing system, variable arrival times, variable work content. It classically matches everything you would analyze in a queuing system. So how do we behave in engineering? We say, well, if I put 10% more work into engineering, it should take 10% more time.
Doesn't work that way.
Is that we'd want to operate as close to, a perfect engineering organization would have no engineer idle for more than 5 minutes in the course of a year. Then we would be doing a brilliant job in managing engineering. When in fact, what you're doing is you're guaranteeing your resources are going to be blocked 99.9% of the time. So if any variability at all showed up, your ability to dispense with, to make that queue go away is very limited because you have zero margin left in the system. And I think it is a huge mindset shift change for a lot of engineering managers to realize that you have to you get your best economic performance when you build capacity margin into an engineering organization. And when you focus only on high utilization of the engineers, what you're silently doing is you're creating work in process. You're creating work that cannot be serviced
stalled.
sitting in queue.
Right.
And when you take into account the cost of that work sitting idle, because that work has a cost to delay. If 95% of your, let's say if 70% of your cycle time was work sitting idle waiting to access an engineer, that's costing you cost to delay dollars in the process. So chasing after that last 5% of engineering utilization is a disaster with respect to queue time. In fact, when you look at the math, basically, if I were to take the capacity utilization rate of an engineering process, as I move it up from 80 to 100%, as I move it from 80 to 90, I double the size of the queue. It's basically, the formula is rho over 1 minus rho. But the key thing is every time I have the distance to the 100% point, I double the queue. So I move from 80 to 90, I double the queue. 90 to 95, I double the queue again. 95 to 97.5, I double the queue again. And so I see this astronomical rise of queuing effects as I take even very small steps towards high utilization.
But it also reflects a very linear, low impact if you have low capacity. So I would assume that there's an inflection point that's optimal.
The efficiency gains are minimal when you're operating there. But no, you're absolutely right. It's a U-curve optimization.
Right.
That's one of the great blessings when you look at these problems quantitatively is you discover there invariably are these U-curves where there are two competing costs that are finite. It might be a hyperbola against a linear function, or it might be a geometric function again. But you see these U-curves, and the great blessing of a U-curve is you don't have to find the right answer.
You don't have to be exact.
You don't need the right answer.
If you're somewhere in the bottom.
Anywhere in that zone, in that optimum zone, you could be 10% either way, and it makes a difference of 1 or 2%. So people tend to think these problems have to be very accurately analyzed at things until they actually analyze them and they discover that they don't have to be.
Right. So looking at queuing from a bit of a different perspective here, you talk about, and you have this nomenclature for, a FIFO, a very serial first in, first out queue, a first in, multiple out queue, or multiple in, multiple out. For our listeners who are thinking about process flow, is there an optimal queue architecture, or how do you decide or think critically about what is the right way to think about? Should I have a matrix organization of engineers with a couple of programs? Should I have cross-functional teams? How do I build a queuing system that also in and of itself doesn't create more work in process queues?
Well, you're actually asking multiple questions.
Yeah, I'm
there,
terrible at that.
and-
Yeah.
and things
We've got
in
all day.
terms that
Yeah.
have the potential to get entangled into an answer. I mean, there are some general principles in queuing where what you would want to do if you had 5 servers and you were asking, should I have a queue of work in front of each server, or should I have a common queue, shared queue, serving all 5 of the servers?
Right.
And mathematically, that's a fairly straightforward problem because the shared queue has less intrinsic variability than having dedicated queues for each server. Now, everybody's experienced that at an airport where
Right.
they'll
TSA
go,
or something.
they'll end up having multiple lines. You're never going to pick the right line
Right.
and things like that. But intrinsically, what happens is, let's say you have these isolated lines, at the ticket agents, and one customer wants to pay for their ticket with pre-war rubles and things like that. Everybody in that line ends up incurring a large delay associated with it. When you have a single queue with multiple servers, that one bad job blocks a single server,
But not
but
the
it doesn't
others.
affect everybody else in line.
So what would that look like in an engineering development process? Is that, so I have the need for mechanical engineering. So it would be better for me to recognize that there's a need for that service and have a variety, more in a matrix form of 5 MEs, as opposed to having 5 teams each with a 1 ME. Is that kind of where that?
Yeah, there are times when you do it
Either way, yeah.
I mean, a lot depends on what is the variability of the demand for that service.
Got it.
If you pretty much have a constant core demand for the mechanical engineer on the program, enough work to keep the guy full-time busy, either working or working ahead, the guy or the woman, then probably putting the person on the program is going to be the optimum thing to do. If you've got real variable bursts of demand, you'll actually get better performance by aggregating a group of people and sort of pulling them on
Yeah,
demand.
more of a
to
matrix
the
kind of a
program.
thing.
More
A pool.
matrix thing. They're not sort of an overall answer to that. And you'll see that, you'll have people like, you'll always have engineering organizations that have some of these specialist skills that you do not want to replicate on every team. Like user interface is a classic one that shows up in software. Do you want a world-class user interface person on every one of your Scrum teams? Idiocy to do that.
Right.
Not only do you not want to incur the cost, but you're going to end up having divergent approaches. Your products will look like they're designed by different companies. So you'll always have situations where you say, it is better for me to centralize this discipline. The killer in most cases of centralizing resources gets back to the metric question as well. Because classically, the centralized resources are being measured by efficiency, which causes them to operate at a very high level of loading, which produces a disastrous response time for the projects.
Right.
Now, I was working with one medical device company. They used to have a tooling shop, and the tooling shop manager was measured on the cost per tool produced for the various projects. The tooling shop manager didn't want to have extra equipment because it raised his overhead rate. He didn't want to send work outside because he liked having a backlog to keep himself busy and things. He didn't want to use overtime because it raised the cost of the tools. So they said, let's look at what the real cost of the tooling is to a program. The real cost of the tooling is how much it delays our program. So let's shift the metric. Instead of measuring the cost of the tool, let's shift it to how much time you're on the critical path of the program.
Right.
So they changed the metric. They didn't change the tooling shop manager. All they did was they changed the metric. Well, the tooling shop manager said, now that I've measured on how much time I'm on the critical path, I'm going to do things differently.
Right.
I'm going to put in another machine tool. I'll send work outside when I'm overloaded. I'll use overtime when the backlog starts building up. And in fact, I'm going to start visiting these people who are requesting tools for me and ask them, can you tell me the rough size of the part you're asking me to make a tool for so I can procure the tool steel ahead of time so I don't have to wait for a lead time on that material. But the interesting thing is, once you shifted to a sensible metric, this dysfunctional behavior of the centralized resource is not responsive went away. And Microsoft did that in software as well. Microsoft would have expert software groups that are servicing many different programs and things. They created what they call service level agreements, SLAs.
Right.
Where they said, we're going to answer we're going to answer, on average, we're going to answer your questions within 24 hours. No more than 5% of the questions are going to take 5 days to answer. And then that service level agreement became a tool for them to talk to their boss about how much resource do they need. We say, now that the work has gone up, we're not meeting our service level agreements anymore. We need to add more capacity.
Right. Fantastic. So I want to talk to you about one other very interesting topic, and that's the concept of batch size and batch size reduction, and a little bit about the future. But first, I do want to share with you one other cool addition to the Hillier Measurements family of messaging and things that we're doing right here.
5G is coming. More data, more connected things, and capabilities we haven't yet fathomed. But already government and universities, base station, handset, and IoT companies, they have all gone to Hillier Measurements for inspired design in research, development, and production test. Why don't you?
All right. Welcome back. So Don, this concept of batch size and batch size reduction. I build test equipment. We come from a background where we would need to design everything before we could test anything, and we've learned that's not the best way to go. But can you give a kind of a basic primer to our audience about the mindset about looking at an overall design project and whether you want to look at it as one single design or remove it into smaller designs? Because this is an area where a lot of what you've got in flow starts to mimic some things that you also see in more of an agile mindset. And I'd kind of like to dig into that a little bit.
Agile is pretty much automatically working in small batch sizes because they work in sprints. Although they never use the term batch size, which is a great loss, because for 100 years we've worried about batch size in manufacturing, and they've lost access to all of that thinking. But I'll give you a classic. For me, the batch size in an engineering process is at a deeper level is the quantity of information or material that changes state in a particular instant in time.
Okay.
And to bring that down to something more practical. So let's say you have to do system test on your system. And you say, well, the only way I have fidelity in my system test is if I test the entire system. So you say, by definition, I can only do system test when the entire system is designed. And that's that is maximum theoretical batch size. You couldn't make batch size higher than 100% of the system. And then what you might do, though, is you might look at that and you say, did we really need to have the full system available for everything that we learned in system test? And so I've worked with organizations where they made a list of every single defect that showed up when they ran system test on their design. And they set a bunch of engineers in the room, and they went item by item through that list and said, did we need to have the entire system available to have found this defect? And a second question, or is there a way we could modify our upstream processes to have extracted that information earlier upstream? And and in fact, they would say the answer would be, in some cases, the answer is somewhat complicated, because they say, look, when you do system test, the system is its own test bed. You don't have to invest in any infrastructure. Right. It tests itself. If we're going to test pieces of the system upstream, we're going to have to invest in testing infrastructure, things like that. But the interesting thing that you discover, and in general, there's been a huge tendency to push testing further and further upstream, is, you get it off the critical path and things. You have less of an explosion when you do the integration at the end of the process. You actually correct problems where you have enough time to test whether the fix actually works, which is a big problem when you're discovering it in downstream.
Rework expense is dramatically lower.
And the other interesting thing you find is when you end up creating this infrastructure for testing at the subsystem level, you're accessing the components in a way that you can often massively increase the speed at which you do testing. Because a lot of times at a system level, events occur relatively infrequently, and you need to accumulate a lot of hours before you induce that effect. And if it's an intermittent effect, it's even harder for you. What I've seen is some people who used to be testing at the system level who move to subsystem level testing, where they basically can break at the interface to a particular subsystem and things like that. They can exercise that subsystem like 10,000 times faster than they can produce the defects when they're testing at a system level. They get these huge increases. Every once in a while, the protocol drops a byte and it crashes the entire system and things like that. Well, yeah, that event occurs once every 100 hours and things when I do it at the system level. But if I rig my test bed at the subsystem level, I can make it occur every 10 milliseconds. And then I can find out what's really going on. So, there are really interesting dividends that come from saying, let's question that assumption that the high fidelity answer is really necessary for everything that we learn from system test. We're never going to put system test out of business. We're still going to need that. But what we'd like to be is in a world where we find 3% of the system level problems when we hit system test instead of 90%.
Yeah, it's certainly the most expensive place to find them at the end in system tests, for sure.
Yeah.
So that was a lot of meat, and I can tell you, and my staff can attend to too, that's still the pregame warm-up to what you have in Flow. When I read through the book, by the way, for those of you guys who don't know, Flow is Don's most recent book, but it's been out for a few years. We talked about this before the show. If you and I have the chance to get together again in 3 years, this is a loaded question. Where do you think the innovation from what you've done in Flow will be in terms of continuing to innovate to be better as a product development organization? And the hidden question in that is where would you go in your next book?
Well, I'm probably, where I'd go in my next book is different than where this book would be.
Oh, fascinating. Tell me.
Because where I go in my next book, it's a book that I've wanted to write, but I never get excited about writing it, is I need to produce a 150-page version of the Principles of Flow that is an easy read.
The Cliff Notes of Flow.
Because what's happening is I got VPs of engineering who are going to the VP of marketing saying, you need to read this book. and it's not going to happen. And so then they have to explain the entire book on a whiteboard to someone. And so what I really need to do is produce a tool that saves people who have read the book from having to explain the book to someone who's
Does that
not
resonate
gonna
with
read it.
anybody here?
And so I need to do that. It's not an exciting project to me because it doesn't break new ground, but I know there's a need for it, and I hope, we were talking a little earlier,
Yeah.
maybe this coronavirus thing
Oh, yeah, it's affording you some time.
will create time that I can sort of fill that need.
Well, I would love to volunteer our staff as your beta
Guinea
prototype.
pigs? Yeah.
Oh, yeah, because we understand what you just explained very well.
Yeah. There are two people, some people say, oh, read Managing the Design Factory first because then you'll understand
That's
how
what I did.
Reinertsen thinks, and then you can read Flow. Dean Leffingwell of SAFE fame says, read the book once, don't try to understand anything, and then read it a second time and try to understand everything. And it's not as glib and silly as it sounds, because if you skim through the book, you see more of the structure of what the overall engine looks like, what the major subsystems are, and how they interact. And it's much easier to actually read the book the second time because everything has been foreshadowed. Issues of batch size have been foreshadowed, issues of queue size, issues of cadence, and things like that. You end up understanding the elements of the system a lot better.
Yeah, I
It's
would
not
say,
like if somebody was trying to explain how a car engine works to you, and they just gave you a little soda straw to look at, and they guided the soda straw around the
Right.
different subsystems and things like that.
I can
That's
tell you
hard.
sincerely, in our organization, it's more of the third way to read that book, which is read one or two chapters and then ponder what that impact is on your organization for 2 to 3 months before you go on.
Yeah, actually, one approach that has been highly successful for people is they use a book club approach, where they
Right.
say, one chapter a week, try to read as much of the chapter as you can, assign one person to make sure that you have at least one person who's read the whole chapter, and then they sit down and they discuss where's the low-hanging fruit for our organization.
Right.
And it gets them through just on a weekly cadence, they get through the chapters. It doesn't become an overwhelming burden to everyone. And they start developing an organizational consensus on where the opportunity is.
So obviously, your book, I can't tell you how many copies of this I've bought, but you can get this on Amazon, right?
Yep.
How else can people learn about you, get in contact with you, utilize your services?
I have a website. A bunch of YouTube and InfoQ videos from things I've talked about in conferences and stuff like that. I appear at conferences from time to time. The book is probably the most common
The best
entry
way to
point
do
for
it.
people.
Yeah, well, I couldn't recommend this enough, and I know for our audience and people around there, coming into this episode, I had a number of people reach out wanting to join in a live stream and come join us in the audience, and so I think you're more popular than maybe a lot of people realized, and I can't thank you enough for coming. You have made a huge impact on our organization, and look forward to working with you in the future.
It's more of a cult book than I mean,
Well,
it's-
we're happy to have you as our cult leader. Don, great to have you.
AE Squared is a Hillier Measurements Town Hall production.
So,
AE Squared is produced by Anthony Longoria. Production support by Christian Zamora. The email address, if you'd like to attend a future taping, is tickets@hillermej.com. Hey, thanks for checking out this week's episode. Make sure you subscribe below, hit the bell, give a 5-star review, tell your friends and family, will you? We love having you come along with us here at AE Squared, and next time you're going to love that one because Brian Moore is going to join us. Brian went from managing Destiny's Child to being an engineer to now being the founder and chief operating officer of Dusik. You're going to love that app. Dusik takes musicians and their art form and brings it to market. You're going to fabulously enjoy that episode. So make sure you're here with us here on AE Squared.